Subscribe to our YouTube channel, Joy Learning TV.
You are welcome once again to Joy Learning channel. With me, Wisdom Agbesinyale. And as usual, you call me Wizzy One. And this is Senior High School R. And this lesson is for you, Form 1s, especially those who are preparing to be admitted into the senior high school. What do we have today? We have been looking at how various scientists have contributed to the development of the atom. We looked at Dalton, and we said that Dalton did not do any experiment with any equipment. It is as a result of chemical reactions that he carried out in his lab, and he came up with his theory. And then there comes J.J. Thomson to discover the electron, and that has given different perspective to chemistry. That then if there is a subatomic particle called electron, then we can perform other experiments to discover more. And there comes Rutherford to discover the nucleus. Whoa, chemistry is developing. Yes. So what next? And that has given us the modern structure of the atom. And don't forget Niels Bohr, who talked about spectral lines as a result of he using quantum mechanics. So let's see the modern atomic structure. And of course, since Niels Bohr talked about spectral lines, then quantum numbers will come and throw more light on such. And that will lead us to how to configure electrons in atoms. So at the end of it, we should be able to identify subatomic particles, their location in the atom. And then we'll look at quantum numbers, how quantum numbers also contribute to the development of the atom. So we have to define quantum numbers, look at the various types as they describe completely the electron energy in a given atom. And then we will end up with the importance of quantum numbers. So let's get rolling. This is a table showing the modern structure of the atom. We have the subatomic particles because they are smaller than the atom. So we have the proton, we have the neutron, and we have the electrons. What are their masses? The proton, the mass of the proton is 1. That for the electron is 1. The neutron is 1. And then the electron is 0. And of course the charge, the protons carry positive charge. That is why it is in the center of the atom, attracting the outermost electrons to itself. So it carries a positive charge. We have established that electrons carry negative charge. So there is electrostatic force of attraction between the protons that is occupying the center in the nucleus and then the electrons that are orbiting the shells. Then the neutron carries a 0 charge, and of course we have established that the electrons, they carry negative charge. Where is their location? The protons, as we have already talked about, is inside the nucleus. And we said that the nucleus contains the protons and the neutrons. So the neutron and the proton are located in the nucleus of the atom. And then, of course, we have already also established that the electrons orbit the nucleus. And don't forget, we talked about collapsing atom paradox, where Rutherford said that the electrons are moving around the nucleus. And we said that any moving particle loses energy. So if it loses energy, then it's going to collapse into the atom. Or the atom will not exist. Then Niels Bohr says the electrons are quantized. And they produce spectral lines when they move from one specific energy to the other. That is what is leading us to quantum numbers. Yes. So what are they? Quantum numbers. Don't forget, for a definition, values and symbols, so they are alphanumeric, the computer people will say, that can be used to describe specifically the energies of electrons in the various energy levels in the atom. Why from these various energy levels? Niels Bohr said that the electrons are quantized, so they are on specific energy levels. So if I have that, like that. So this is energy level 1 and then energy level 2. So at energy level 2, what happens? Energy level 1, what happens? So that is for the definition. We are going to use values and symbols to describe that. So this is a flow chart on the quantum numbers. We have 4 quantum numbers, and these 4 quantum numbers will tell us about the shape, the magnetic moment, the spin of the electron, the energy level of the electron, and so on and so forth. So the first one is the principal quantum number. The principal quantum number, we are going to look at them one after the other and look at them as we will apply in electron configuration. So the principal quantum number has to do with the various energy levels of the electron, as Niels Bohr has stated. So if I have that, then I have that. So this is energy level 1, energy level 2, and so on to the last shell that is containing electrons we call valence shell or valence electrons. Then we will also talk about the angular momentum. The angular momentum is divided into 4. This one is talking about the specific orbital. And then since Niels Bohr said the atoms produce spectral lines, then the spectroscopist came up that the lines, some are sharp, and that is S, some are principal, and some are diffused, and some are fundamental. And that will lead us to the SPD electron configuration. Then we'll talk about the magnetic quantum number or magnetic moment of the electrons, and we'll see how the electrons are spinning within the energy levels of a given atom. So we're going to look at them one after the other, throw more light on it for the examination purposes. So the quantum numbers, number 1, will describe the position or energy level. As Niels Bohr said, they are quantized. So we have specific energy levels for electrons within the atom. So energy level 1, energy level 2, energy level 3. And that is the principal quantum number we represent as n. So if I say n equal to 1, then we are talking about energy level 1, n equal to 2, energy level 2, n equal to 3, energy level 3, and n equal to so on and so forth. Then we'll talk about the shape or the type of orbital. So as we saw already, the S, P, D, F. Who are they? So the quantum numbers will also describe the shape or type of orbital. Is it the S orbital? Is it P orbital? Is it D orbital or F orbital? Then we'll continue with the magnetic moment of the electrons, that is specifying the orbital in which the electrons are located. Then we'll see how they are spinning. Are they spinning clockwise or they are spinning anti-clockwise? All these will be made known to us in this lesson. So let's see. You have to know the definitions. So we'll be looking at the definitions. The principal quantum number, that is the n, the value n. So this describes the electron shell or energy level of the atom, or it describes the main shell in which electrons are found in the atom. So in junior high school, you were told that the electrons are in shells. So I have the nucleus there, then there is an electron there, that has 2 electrons. Then this one will have 8 electrons. So it is the principal quantum number that describes the shells. So I have shell 1, shell 2, shell 3, shell infinity. Right. So the value of n ranges from 1, as we have already seen, to the shell containing the outermost electrons of that atom. So let's take lithium, for example. Lithium has 3 protons. And of course, for a neutral atom, the number of protons equal to the number of electrons. So if it has 3 electrons, then it has 3 electrons. So if I want to arrange them, as you know from junior high school, the first one will take 2 there, and then the last one will take 1. So we'll have n equal to 1, that is energy for 1, and then n equal to 2. So that is the meaning. The n ranging from 1 to the shell containing the outermost electron. So the n equal to 2 is the shell, the last shell in the atom lithium. So that is the valence shell or the outermost shell. If I have, for example, sodium, then I can have n equal to 1 there, n equal to 2, and n equal to 3. So here I have that, 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 then I have that. So n equal to 1, energy level 1, n equal to 2, energy level 2, n equal to 3. So it means that sodium has 3 energy levels and of course 3 shells. So continue like that from junior high school. Now, what is it so much about the energy level? N increases, the orbital extends, as we saw. Look at lithium. Lithium has only 2 shells, and then sodium has 3 shells. You see? So that is the meaning of the statement. So as n is increasing, the shell is also increasing because we are increasing the number of shells. So if we have more shells, then it means that your size or the atomic size is also increasing. And don't forget, I said earlier that the nucleus has a positive charge. It is attracting the electrons to itself. So if you are near to it, it will hold you tight that you can't do anything. But as you are moving away, there's freedom to run away from the attraction of the nucleus. That is why we are saying that as you are moving away from the nucleus, you increase in energy. So the electrons that are further away from the nucleus, they have more energy, therefore they can run away from the attraction of the nucleus. You see, just like your big sis and your little sis holding you. So the little sis, she is not strong enough, but the big sis, she is strong. So if she gets hold of you, you'll find it very difficult to get out of her hand. But if the little sis holds you, little effort, you are off. That is how the energy of electrons are also behaving. That as they are moving away, as the shell is expanding, so it means that the valence shells will experience lower energy. So any electron in that shell can easily run away from the attraction of the nucleus. So if I have electrons, for example, this is energy level 1. Then this is energy level 2. If I have energy level 2, all electrons there can be described as in the same shell. All electrons, they are in the same shell because you have already learned from GSS that these are shells. So whatever electrons are located there, they are in the same shell. This will be clear when we start electron configuration. So this is what you will need to fill the shells of the atoms. This one is just junior high school. We are just reminding ourselves from junior high school, then we'll build up for the current purpose of what we are learning today. So all these, they are just a recap, and it should not be difficult for you to keep. Very, very important. Take note, please. We said if you are moving away from the nucleus, you are increasing in energy. So it means that n equal to 1 is the lowest, or the electrons there have lower energy. Why is this so? Because they are held tightly by the nucleus. So there's no way you can run away. That is what we mean by you have lower energy. So all electrons in the energy level n equal to 1, they have lower energy because they are tightly held by the nucleus. So you will need a lot of energy before you can take it away from there. Then take note of this. There is a wide gap between the lowest energy level and the next energy level. What is that? This is the first energy level, n equal to 1. The electrons there, they have lower energy. So if you want to take electron from there, you need a lot of energy. But in energy level 2, there is a wide gap. Energy level 2. You see? So the gap there, it means that it will be easier to remove electrons from energy level 2 than energy level 1. Now, as you are increasing, the electrons are gaining more energy, so they can easily escape the attraction of the nucleus on them. The next thing that we want to look at, angular momentum. This describes the shape of orbital type, and it is represented as L. Please, these variables are very important. We'll be applying them. Describe the shape or type of orbital. Is it S? Is it P? Is it D or F? It determines the subshell within a principal energy level. So what is there? If I say energy level 1, that is n equal to 1. What type of orbital is there? If I say n equal to 2, what type of orbitals are there? That is the function of the angular momentum. So anytime you mention a value, you know the orbital associated to it. So if I say the angular momentum value is 0, then it is the s orbital that is associated to it. Don't forget, we are going to apply them in electron configuration. If I say the value of L is 1, then I'm talking about the p orbital. That's how we say it describes a specific orbital. Then L equal to 2, it describes the D, and then 3, it describes the F. So what is the name of the orbital when angular momentum is 0? It is the s orbital. If it is 1, it is the p orbital. If it is 2, it is the d orbital. If it is 3, then it is the f orbital. I don't think this is so difficult for you to keep. Okay, let's continue. Now, N and L will relate. How? The value of L ranges from L equal to 0 to L equal to N minus 1. That is how they relate. So that at energy level 1, that is N equal to 1, L will be 0. So at energy level 1, if I have that, N equal to 1, L will be 0. L will be 0. Now, if L is 0, what is the name? It's S. So it means that at energy level 1, only the S orbital that will exist there. Follow carefully. Energy level 1, only S orbital will exist because we have labeled the S orbital as angular momentum value 0. So at energy level 2, what do you think will happen? So at energy level 2, L will be 0 and then L will be 1. So it means that at energy level 2, L is equal to 0 means that there is S orbital. And then L equal to 1 means that there is P orbital. So at energy level 2, there is S orbital and then P orbital. Follow carefully because we are going to apply them to get it. So as I said, at n energy level 1, n equal to 1, then we'll have s orbital. Only one shell that exists there. So this shell is the s orbital. Then we have seen that energy level 2, there will be L equal to 1, N equal to 2. So there will be L equal to 1, there will be L equal to 0. So there will be s orbital and p orbital at energy level 2. So this tells us that in any given atom, there are s orbitals, and then the rest will follow. Because there will be energy level 1 for all atoms. Even hydrogen, being the smallest atom, will have energy level 1. So if I have lithium, Li, Na, all sodium and lithium, they will all have s orbitals, and then the rest will follow. Right, so we have already established the fact that if n equal to 1, it means that there is one shell. If n equal to 2, there is the first shell, and then the second shell, and so on. If n equal to 3, then it means that I have first shell, second shell, and then the third shell. So I have 3 shells when n equal to 2. That is why we said that the number of subshells in a given shell is equal to the value of n for that shell. So you can do a lot of exercises on this. So to designate a particular subshell, the principal quantum number is written first by the letter code for the subshell. Because we said that quantum numbers, we use values and symbols. So for example, if L equal to 0, it means s orbital. And then n equal to 1, it means first energy level. So I can write 1s. The 1 there is a principal quantum number, n equal to 1. Then the s there is telling us that the angular momentum is 0. So we have 1s. If I say n equal to 2, n equal to 2, and then L equal to 1, it means that I'm at energy level number 2, and then L is equal to 1 is the p subshell or the p orbital. So to represent that, I'll have 2p. If I have n equal to 1000 and then L equal to 1, I'm going to have 1000p. Because 1000 is the principal quantum number, n equal to 1000. And then the p is the value of L being equal to 1. So that is how we write the letters. So take note. So if we are given the n value and L value, we should be able to describe that orbital, the energy level in which it is located, and then the type of orbital in that particular energy level. So the subshell with n equal to 2 and L equal to 1 is the 2p, which we have already discussed. So if I say n equal to 4 and L equal to 0, then that will be 4s. What about if I say n equal to 4 and then L equal to 1, what will it be? It's going to be 4p. What about if I say n equal to 4 and then L equal to 2? It's going to be 4d. Then if I say n equal to 4 and then L equal to 3, it's going to be 4f. Oh, is this not interesting? Will it be too difficult for you to keep? No, no, no. What about if I say n equal to 5 and then L equal to 0? That will be, yes, you got it there. Yes, so it's going to be 5s. What about n equal to 5 and then L equal to 1? So that will be 5p. You see, and it's very simple and straightforward. So you can describe mode of such. So the value of L affects the energy in the atoms with 2 or more electrons. The subshell within a given shell differs slightly in energy. Very important. If I say n equal to 2 and then L equal to 1, we have 2p. And we said that in all atoms, there is an s orbital. Because if n equal to 2, we are going to have L equal to 1 and then L equal to 0. So we are going to have 2s and then 2p. So with the 2s and 2p, the s here and the p, they have the same principal quantum number, that is 2. So it means that they are in the same shell. So first shell, second shell. This is n equal to 1. N equal to 1 has only s orbital. N equal to 2 has 2 orbitals, the s orbital and the p orbital. So it means that any electron that is in the s orbital and then the p orbital, they are in the same shell. So if they are in the same shell, then they will vary in energy slightly because they are not in different energy levels. They are in the same energy level but located in various orbitals within that energy level. So if you are assigning energy level, it will affect all of them, but they will differ slightly because they are located in different orbitals. Is that right? Yes. So here n equal to 4. So there will be 4s, there will be 4p, 4d, 4f. So they increase in energy in that order. So in the fourth energy level, the s orbital is less in energy, followed by the p, followed by the d, and followed by the f. Why? Because if I have the energy level 1, we establish that it is only the s orbital that is there. And then energy level 2 and so on and so forth, they are increasing in energy. So at the fourth energy level, F will be in the highest energy. So whatever electron is located there can easily run away from the attraction of the nucleus. So that is how they increase in energy. The next one, we have the magnetic quantum number. For a definition, describes the orientation of electrons in orbitals in space. So how are they positioned? How the electrons are being positioned is described by the magnetic quantum number, or the specific orbital or cloud within the subshell and use the projection of the orbital angular momentum, that is L, along specific axis. So before we get there, the specific axis, the PDF, when you place them in strong magnetic field, they split. So the P here split into 3. And then they are directed along specific axis. So these 3 will have that. So this is Y, this is X, this is Z. So they will be directed along the Z axis like that. So that is why we will get to know that the P orbital has a dumbbell shape. So when it is split into 3, there is one in the x-axis, there is another in the y-axis, there is another in the z-axis, forming a 3-dimensional structure or shape described as dumbbell. The dumbbell, you can find it in your kitchen. They're what we call tapoli, if you know. Not the tapoli that if human being dies, then they will erect it for you to sit under. No. The one you use to grind pepper. So if you help mommy in the kitchen, you know what I'm talking about. Like that. You use it to grind pepper. So it looks like a dumbbell. So these are everyday things you can use to describe the shape of the P orbital. There are more. When we get to shapes of orbitals, I'll tell you more. Is that okay? Yes. So let's continue on that. Take note, its value indicates individual orbitals within a subshell. It is related to the way the individual orbitals are oriented relative to each other in space, as I have already shown you the P orbital. And these P orbitals directed in the Y, X, Z, they are perpendicular to each other. And that is described by the magnetic quantum number. So atom is placed in a, which I have already talked about, that if the atoms are placed in strong magnetic field, they split. So the P will split into 3, the D will split into 5, and then the F will split into 7. But with the S, the L value of L, which L is 0, describing the S. The S is not directional. So when we get to orbital shape, we will say it is spherical. So it cannot be directed into any way. So that's there. So the value of M or M sub L ranges from plus L to minus L. So whatever value you have is from plus to minus. So as we have already said, S subshell, L is equal to 0, which we have already talked about, and it contains only one orbital. So the magnetic moment of electrons is 0 in the S orbital. Magnet. Why are we saying magnetic moment? So magnetic moment, when a charged particle is oriented, we are talking about the strength and then the orientation of a charged particle as a result of the electron field that it's created. That is telling us that when a charged particle is moving, it creates electric field. And that is the principle on which your fans in your home work. The electric motors work. So as the electrons are flowing, electricity, it creates magnetic moment to turn the fan or to turn the electric pole, the electric motor. Okay. And the same way, magnetic fields also can create charged particles, and that also has its uses. Right, so as we said, they are directed along the X, Y, Z axis, depicted as dumbbell shape. We talked about that already. So M of an electron in a p subshell will be that, because we said that the value of the magnetic quantum number ranges from plus to minus. So because of the three orientations of the dumbbell shape nature of the p orbital, they will have the magnetic moment in a negative manner, in a zero manner, and in a positive manner. So if the p orbital is oriented along the x and y axis, then one orbital will have L equal to 1, because the L value of p is 1. So we'll have L equal to 1. And then the M sub L will be 1. So M value will be 1. And then the other one will be L equal to 1 and M value will be 0. Then the last one, L equal to 1, M value will be negative 1. So that is how we describe that. Take note. We are going to apply them. So take note well. So if it is the D, then we know that for the D orbital, the L equal to 2. So if L equal to 2, then we are going to have M sub L will be minus 2, and then L equal to 2, M sub L will be minus 1, and then L equal to 2, M sub L will be 0, L equal to 2, M sub L will be plus 1, and then L equal to 2, M sub L will be plus 2. So it has 1, 2, 3, 4, 5 orbitals oriented in the axis dx, dxy, and then dzx, dyz, dx squared minus dy squared, and then dz squared axis. Please, this one is for your knowledge. What we should focus on at this stage is on the s orbital and then the p orbital. As the orbitals increase, or as the value of L increases, the orbital orientation becomes more complex and complex and complex. So you can just type on the net and then find the shape of the D. You see how beautiful it is. Then you go and look at the F, the shape of the F orbital. You see that it's getting more complex and more complex. So for the F, we say it splits into 7, where L equal to 3. So one will be L is equal to 3, and then M sub L will be negative 3. Another orbital will be L equal to 3, M sub L will be negative 2, and so on. So we are going to have 1, 2, 3, 4, 5, 6, 7 orbitals. These orbitals so splitted in a strong magnetic field of the PDF, we call them the degenerate orbitals. Take note. The last thing we want to talk about on the quantum number is the spin quantum number. The spin quantum number describes the spin of the electron within an orbital and gives the projection of the spin angular momentum, that is L, along specific or specified axis. So the spin only takes two values. You are either spinning clockwise half or you are spinning anti-clockwise half. So the spin is plus half and minus half. Or you are either standing or you are lying down. You get, so that's all about the spin quantum number. How the electrons, if we say spin, then it's on its axis, right? Then they specify the direction of spin of an electron on its own axis. It assumes two possible values. It's either plus half or minus half. Clockwise or anti-clockwise. Or spin up, spin down. So in any given orbital, the electrons are there. You are either spinning up or you are spinning down. The reason is that when you are spinning clockwise, you are creating magnetic field. When you are spinning anti-clockwise, you are also creating magnetic field. So there is negative magnetic field and there is positive magnetic field. So at the end of the day, there is no magnetic field existing within a given orbital. So that tells us that in any given orbital, you can hold a maximum of 2 electrons. And you holding a maximum of 2 electrons, the electron is either spinning clockwise or anti-clockwise. So at the end of the day, there is no magnetic field within the orbital. That leads to orbital stability. It's very interesting, right? Yes. Okay. Right, so there are 2 components to the magnetic field associated with electrons in an atom. So one is the moment of the electron around the nucleus. And the moment is just describing the magnetic field created as a result of the orientation of the electron. And then the strength of the field that is being created. So, and then the spinning of the electrons on its axis. That is what happens within a given orbital in an atom. So if we have all the values of NL and M and of course the spin, we should be able to describe the orbital. Or if we are given the configuration, we should be able to give the values of the quantum numbers. So each orbital can contain a maximum of 2 electrons, which I have said, and they have identical N, L, and M. So if you know these values, you should be able to write the configuration of. So if we want to have some illustration, we want to describe an electron in the 2p orbital, and of course of carbon atom. So because it is 2p, then N is the second energy level. That gives us 2. Then L will be 1 because we are talking about the p orbital. And of course we said that the M or M sub L is a +1, 0 or -1. And then the spin, it's a positive half. So if I want to use the electron box configuration to describe what we have here, then we say it will split into 3. So 1 there. You see. So since we move from negative to positive from left to right, so I can say this is -1, 0, +1. Now this is 2p. So L is the p. And so it's spinning positive. Then we have 2 electrons in the outer shell of the carbon in the 2p. So since we are spinning positive, it means that I'll have that and that. You see, so it means that the M sub L will have that, the 0 value, because the last electron is in the M sub L, the 0 orbital. So we can talk more about this. We can have more examples. So the same way, if I give you a configuration, you should be able to state the values of the quantum numbers. You should be able to state the value of N, value of L, have value of M, and then value of S. Okay. Let's define these ones. Very, very important. We talked about a shell. So a shell is a group of electrons in an atom with the same principal quantum number. We have seen. So if I say 2s and then 2p, this is a shell. That is energy level 2, because they have the same principal quantum number. Then the subshell is a group of electrons in an atom with the same angular momentum. That is L. So that's a subshell. Orbital, volume or region of space around the nucleus of an atom where there is a high probability of finding one or more electron. So in GSS, you were told that we have that electrons. This doesn't mean that if you pick the atom, the electrons will be arranged like that. You will see lines like that, and then you see those crosses on. No, that is not. It's just a probability. That is why we say volume or region, where there is high probability of finding an electron. So if you want to appreciate it well, when in the night or during the day, light a torch, put paper on it, and see the pattern of the torchlight. It shows a highlighted area, and that is how the atom exhibits itself under electron microscope. So you see a highlighted area, then you know that there is possibility or probability that those areas can contain electrons. Or you can say region or space in which electrons are most likely to be found around the nucleus. So you pick one for yourself for an examination purposes. So orbital is a shell with a given set of principal angular momentum L and magnetic quantum number. So 3 definitions for orbital. Pick one for yourself, and that will be part of you. Then the last one, we talk about degenerate orbitals. Orbitals with the same or similar energy. So the P, D, F, they have degenerate orbitals. The P has 3, the D has 5, and then the F has 7. And if they are, each degenerate orbital is containing 2 electrons, you can determine the total number of electrons these orbitals can hold. So if it is 2, then 2 times 3, that will be 6. 5 times 2, that will be 10. And then 7 times 2, that will be 14. The last thing, quickly, we talk about the importance of quantum numbers. Number 1, they determine the shape of the orbitals of atom, or specify the shape of atomic orbital. That is L. Is it S orbital? P? What are they? We say S is spherical, P is dumbbell, and so on and so forth. They strongly influence chemical bonds and bond angles. So here it will come clear when we are talking about chemical bonding. It specifies the orientation of electrons in an orbital. So you can even identify the specific quantum number that is responsible for this. So spin and opposite spin, you tell me that it is spin quantum number. Then they specify the particular orbital. They specify that a particular orbital can hold a maximum of 2 electrons. That is why we can comfortably state the number of electrons that can be held by a given orbital. They specify the number of electrons a particular subshell can hold. So the subshell, let's say the degenerate orbitals, they hold 1. So the p subshell will hold 6. The d subshell will hold 10. The f subshell will hold 14. Then determine the size of the orbital. We talked about the principal quantum number. When it increases, the size of the atom also increases. Yes, so that's it about quantum numbers. And now you know how the modern atom looks like. It contains subatomic particles. So you must know their charges, know where they are located. Then we must know how to define quantum numbers. We say we use alphanumeric. They are values and numbers to completely describe the energies of electrons in orbitals. So look at the 4 quantum numbers. We are going to apply them in electron configuration. Then we also look at the importance of quantum numbers. At least you should know 3 of this, so that whenever you are called upon to state 3 importance of quantum numbers, you should be able to state them without sweating. This far we can come. Enjoy learning, we enjoy learning. So if you want to enjoy learning, then always don't forget to tune to Join Learning as we enjoy chemistry together. With me, Wisdom Agbesinyal. And never forget, I will respond very well when you call me Wizzy One. Take care and keep on learning on Joy Learning channel. Till we meet again, it's Wizzy One. Bye-bye.
Subscribe to our YouTube channel, Joy Learning TV.